we have to restrict the problem domain in some way in order to achieve interactive frame rates. So we can either reduce the resolution on which we run these global illumination calculations and get a lower quality result, or we can ensure that parts of the problem are static, such as geometry or lights. So depending on how we limit the problem, we'll get a trade-off in quality, because a completely dynamic solution will often require updating on every frame, whereas a partially static solution may permit us to reuse calculations across multiple frames, permitting us to spend more time on those calculations and have a higher quality result. And that's what we have in this graph here in the lower left. We have both static geometry and static lighting. If your game is fully static, that's great, because we can throw as many pre-computation resources as we want into generating very high-quality light maps with a lot of detail, and we'll get extremely high-quality lighting as a result. Now, at the other end of the scale, if we let both geometry and lighting be fully dynamic, then we have to recompute on every frame, which precludes us from pre-calculating or reusing any calculations. So as a result, in order to maintain that interactive frame rate, we have to do very low resolution calculations, and that results in a low quality global illumination result. So here I've taken the graph and marked off a few popular global illumination techniques that we commonly see in games. In the top left, we have real-time radiosity. At runtime, the lights can be fully dynamic, if the radiosity algorithm is fast enough, that is, although in reality, the global illumination resolution has to be somewhat limited in order to maintain good performance. Now, in the same category of fully dynamic algorithms, we have precomputed radiance transfer. That's very similar to real-time radiosity, except we pre-compute the light transfer from distant light sources like the sun and the sky. We can't do point lights, only directional lights that are far away. The major cost here is the size of the pre-computed data, because we're pre-computing data for many different directions. And also that the model is mostly of use only for outdoor scenes, because of the limitation to distant light sources like the sun and the sky. But it is very effective for MMO games or outdoor games where we need support for time of day. Now, moving to constrained algorithms, in the top right, we have light propagation volumes, which are very popular nowadays because it is still a dynamic solution. The major drawback here is that because it is fully dynamic, the resolution needs to be limited. This can result in lighting bleeding through walls. So what you essentially need to do to make this work is you have to fine-tune and adjust the geometry in your scene so that the walls are positioned strategically to account for the light propagation volumes and prevent bleeding through walls and other strange artifacts from being a problem. Now, both of these two methods require a lot of CPU horsepower. So before using them, you really need to think about whether, first, you have the CPU budget in your game in order to do these kind of calculations, and whether or not those CPU resources would be better used in other parts of your game, like AI and particles and physics. Now, in the bottom right, we have irradiance volumes. This is more of a pre-computed method where we pre-compute volumes of spherical harmonics, or basically cube map samples, that can be used to light dynamic geometry. So the lights are static, the position of our lights are fixed, but geometry can move around. And this has been seen recently in games like Far Cry 3, where an automatic system of irradiance volumes was used to light all of the vegetation and props in-game. It's also great for cases where you have characters running around the level and you want them to receive effects from global illumination. Now, moving on to the bottom left, this is my favorite case, traditional light maps. The benefit here is that they are extremely cheap to look up in-game. It's just a texture fetch. Very little runtime impact. You can spend as much time as you want pre-computing light maps, run it on a render farm. You've got unlimited CPU resources. So these light maps can be very high quality and contain a great level of detail. And its pre-computed lighting is perfect to save a few cycles for enriching the user experience in other areas like your particles, your AI, or your physics. Now, in this diagram, we can see where Beast fits into all of this, all of the red boxes. So Beast is essentially about pre-computing lighting data, so there's no runtime component. It covers all of the areas where part of the problem is static and thus possible to pre-compute. So we can touch on most of these algorithms except for the light propagation volumes, which is sufficiently low resolution on today's hardware that you really want to think twice if you want to use that in your game. So at the end of the day, what you end up shipping in your game is the pre-computed, baked rendering results from Beast, and then the game runtime handles combining these results with the rendering process during the game. So what makes Beast really unique is not so much about the whole runtime experience, but that it radically changes your workflow during production. There's no longer a reason to choose a lower quality dynamic technique for artist and workflow reasons during development, because Beast can leverage a render farm or the Autodesk A360 cloud service to interactively light the scene that your artist is working on with high quality, path-traced lighting and fully dynamic geometry and lights. What's unique about this approach is that we are baking actual light maps and actual vertex colors so that you can preview and tweak the data that will actually ship with the game, allowing you to spot problems and make adjustments early on in production, as opposed to the artist can just look at a rough preview approximation. And that's the reason that we've surrounded this whole graph in blue here. Because although you can't do fully dynamic stuff at runtime in your game with Beast, you can have fully dynamic lighting for the artist as you're building your levels. And Beast does this by leveraging multiple computers, either a local render farm that you have in your studio, or resources that we have in the Autodesk A360 cloud to quickly render high-quality, fully dynamic global illumination. And this is going to be a lot more accurate than trying to real-time approximate radiosity. So let's step back and ask ourselves, how does this fit with my game? Where in the diagram does my game fall? What does a typical game look like? The truth is that your game will probably have all of these combinations of geometry and light. You'll have parts that are static, but you'll probably also have some dynamic parts. So what I really want you to take away from these slides are the techniques that we've mentioned here should not be considered as mutually exclusive. You don't have to only use light propagation volumes and nothing else. These techniques are complementary to each other. So let's consider a city scene where we have a completely dynamic global illumination solution running on the whole scene. If we use GI on the entire scene, we're going to waste a lot of cycles on faraway objects that may not even be dynamic. Instead, let's apply the dynamic GI solution only where we actually need it, to nearby objects that are in the foreground and have a big impact on the game player's perception of the quality of our game. We can use that cheap pre-computed lighting on faraway objects in the distance to save those valuable CPU resources for something else. So for the next generation of consoles, I think that fully knowing where to take advantage of the benefits of these techniques is what's going to make the difference between games that truly shine and games with average lighting. The next generation of hardware will not give us an infinite amount of processing power. It may very well be a lot faster, but even that being the case, game players are going to demand more from this hardware. They're going to have higher expectations, meaning that lighting still needs to be lighting still must be optimized to maximize what the platform can deliver. So first, excuse me, let's go over the benefits of pre-computed lighting. High-quality lighting. The most expensive path-traced global illumination is going to be just as cheap to evaluate as a bad, low-quality light map that's rendered with only direct lighting. You can essentially store down anything you want into a light map. You can run caustics, the most expensive 10-bounce final gather algorithm you can think of, physical soft shadows, and you can take as much time as you want to generate a light map since it's all done offline before you publish your game. Another benefit is that we have extremely good runtime performance, since evaluating lighting at runtime is nothing more than a simple texture fetch. Performance is going to be very predictable as a result of that, and it's consistent across platforms. Pre-computed lighting scales very well across different platforms. So we're here in the mobile track, and for a mobile game where we're targeting iPhone or maybe a lower-end console platform like Wii U, all we have to do to target different platforms is to scale the light map resolution and push that onto the target. The lighting it represents is still the same, consistent across platforms. It's just scaled down to fit the memory capacity of each platform. Now, of course, there are some drawbacks for pre-computed techniques from a production point of view. The pre-computation time can often be painful workflow-wise. The artist has to wait while results are baked and generated before he can see the results of his edits. However, with the Autodesk A360 Cloud and Beast's up-and-coming cloud baking feature, this will be less of an issue. Memory usage is another big one. Pre-computing lighting for a huge scene can easily take up gigabytes of texture memory. So it typically requires you to implement some sort of a streaming solution to pull in those light maps on demand. So taking a look at Beast, Beast is a game pipeline tool that is meant to work as a toolbox for pre-computed lighting. It bakes offline lighting data for games. It only pre-computes data. There's no runtime whatsoever, and this means it's completely platform independent. Beast is integrated into your own level editor through a C API that's reminiscent of OpenGL, although it's a little more object-oriented. We have integrations for Maya, Max, and Unreal 3. Backing Beast up is a distributed rendering system that you can install on any workstation in your studio. This enables you to leverage idle cycles on your coworkers' machines in order to bake light maps faster. And again, this is something that the Autodesk A360 Cloud will be addressing moving forward. And making Beast unique is the artist workflow tools we have for interactive light editing. And we're going to see a demo of that in a little while. So new features in Beast 2013. Live scene authoring. Basically, everything in the scene is now live, meaning that the artist can move and deform geometry, alter UV maps, for example, change lighting materials, tweak bake settings, do all of this in Max or Maya, your level editor, and see the updates on the screen on the fly. We have live frame buffer rendering. We added a mode that does final frame rendering. It basically ray traces an image from the point of view of the camera, which enables artists and designers to preview the scene before setting up UVs and light maps. Programmable shading. We have replaced the old fixed function shading pipe with a programmable, physically based one. This allows for higher quality bakes since our materials can now be much more complex. Live and offline global illumination backend. When using this new physically based pipeline, the results between final and preview are much more accurate because we're now using the same renderer in both of them. We've updated our Maya plugin to reflect all of this. And finally, this is a really big feature that a lot of people have been asking for, which is UV unwrapping. Previously, in order to use Beast, your artist had to go and create a whole new set of UV coordinates on your objects for the light map, or you had to use an external tool, or your artist had to do it manually. Beast now does this automatically, and it does it with pretty high quality. So that's our new features. And let's now take a look at a demo of this new and improved UV unwrapping feature. So here we have Maya. What we're going to do is first we're going to run the automatic UV mapping that's built into Maya so we have something to compare it with. So we see here this is our UV unwrapping. There's a lot of empty space here. It's not a very efficient unwrapping. It's okay, it'll work, but it's just not great. Now we're going to do Beast UV unwrapping. Take a minute to set up the parameters here. And here's the result. You can see it's a much denser map, which is going to be much more efficient with your memory usage. An artist could do better, but it's pretty good, and if you have a lot of assets in your game, it's a great way to save time. So that's UV unwrapping, a new feature in Beast 2013. Now let's look more into the workflow benefits that Beast brings to artists, because that's really a big part of what Beast is all about. It's about improving your production pipeline and improving your efficiency while authoring. So what we have here is the classical lighting workflow for precomputed lighting, where you edit your lighting without any real preview of what it will look like in the end. Then you do an expensive bake step here in the middle, and you wait for a couple of hours to get the results back, and then you look at the results. You validate them. Odds are you're going to need to tweak it, move some lights around, change things, change your light map resolutions, and we have to go back to the beginning, start the whole process over again. This can be a very time-consuming process. It's going to slow down your artists and your level designers because they have to wait every time they go and change something. So here's what Beast brings to the table. With the interactive lighting tool in Beast called ERNST, we can turn this around into a much faster, easier, and just more interactive and iterative workflow. The light maps are generated continuously on the fly so that you can iterate on lighting and geometry and get immediate feedback of how the lighting changes and how your level now looks. And this enables artists to try out different things, different placements of lights, and change all of these parameters in real time. And we're going to see this demonstrated in a video in just a moment. Now, mind you, this is only at edit time, But at the end of the day, when you go and publish your game, Beast provides is pre-computed lighting data. But this real-time lighting preview can make your level design workflow a lot faster and a lot easier, and you can get your game out the door a lot quicker than you could otherwise. So ERNST is this interactive lighting tool. It's basically a plug-in, a component of Beast, and it focuses on previewing the actual baked data that will end up in the shipping game. ERNST can be used as a standalone editor with very minimal integration work. It's a what you see, what you get editor. But also you can integrate it with your game's level editor to stream in camera views and to stream in light maps on the fly. So there's basically two ways to integrate. You can use ERNST as is, which is a quick and easy way to start and to get up and running. And if you really get into it and you like it, you can take that to the next level and do an integration with your own editor and your own tool chain. So how can it be interactive? In order to make all of this work, because final baking can be a very time-consuming process, and on a single computer it would take hours, what we're going to do is, how we're going to do this real-time preview. So first and foremost, ERNST limits the work that we're rendering to only what's visible. We won't render objects that are behind us or to the side, only what's in the camera right now. So that sort of view frustum culling saves a lot of time. It also uses brute force, high-quality path tracing that gets a rough result initially, but it rapidly refines to high quality. So one of the things we'll see in these videos in a moment is it will start off with a very blurry image, and then multiple passes will happen, and over a period of a couple of seconds, it'll become sharp and clear. ERNST also takes advantage of any idle workstations in your studio, distributing all of the work between many machines, and potentially an in-house render farm, if you want to set that up, or even the Autodesk cloud. So because we're using all of these compute resources in a distributed way, this isn't just a crude approximation of global illumination, it's the fully path-traced, accurate GI that our artists can preview. So here's a demo of an editor integration with Unreal Engine. So what we have here is the Unreal Editor. This is our light map preview. It's a little bit dark on the projector, but what we have here is all the light maps, and they're being streamed in continuously. So the takeaway from this video is we're going to change various parameters here, like brightness, and gradually we see all of these new light maps stream in over a period of a couple of seconds. While this isn't absolutely real time, it's close enough for the artist to rapidly iterate on the level. So we have this shadow here, and again, it's hard to see on the projector, but this shadow is kind of coarse. The light map resolution is too low, so we're going to bump it up, and in streams the refined texture. So now it looks a lot sharper. And with ERNST built into the Unreal Editor, the artist can play with different light map resolution values and keep trying different things until he finds one that works. So we're just trying some other things with that same shadow. We'll make some change to the light source radius, and that affected all of those light maps. We're adding in some indirect lighting here, and again, new light maps with color stream in. Takes into account the bounce from these green lights. Changing our skylight here a little bit. And that has a big effect on the whole scene. not just an incremental change to a few light maps. We're actually recalculating the whole scene in the background across multiple computers or in the cloud, and it's being streamed down to our system. And so this is how our scene looks like with the final render. So that's Beast in Unreal Engine. And new in Beast 2013, we have a revised Maya plugin, complete with source code. A lot of game developers have asked for larger scale examples of how to do an integration, like the one we just saw with Unreal. And what this Maya plugin is exactly that. It's a giant sample. It's reference source code. You can use it in production, and you can take this code and modify it to integrate with your own editor instead of with Maya. This plugin integrates ERNST into the viewport, so you can model, create lights, UV edit, things like that, while having Beast bake or render the scene interactively in the background across multiple computers. And this is also a great way to evaluate Beast without spending a lot of valuable programmer hours hacking with our API. Just give it to your artists, let them play around with this plugin, see if they like the results you can get with Beast, and the 2013 version has been updated to run only the physically based plugin, so it's going to give you real high quality rendering results right in Maya. So let me show a video of frame rendering in Maya. Here we have Maya and our light maps. And this is where we're going to see the camera angle moving around. And every time the frame updates, it starts out real pixelated and blocky. And as those render results come in over the network from other computers in your office, in your render farm, or in the very near future, the Autodesk A360 cloud, we'll see it progressively update, just like we're seeing here. So we're rotating around a little bit, seeing the scene from a different angle, and it clears up after 3 or 4 seconds. We're going to move this big light in the center here. And we can see it having an effect on the ground around it. And what we're getting here is not just an approximation. It's not one of those new real-time radiosity algorithms. This is actual path-traced, ray-traced quality lighting. Just like what you'd see in-game if you bake light maps. So this is our Maya plugin, new and improved Maya plugin. And now let's talk a little bit more about baking in the cloud. So mobile game teams are typically just a couple of people. And you may very well have very limited compute resources, so you'll want to offload that to our cloud. In order to fully benefit from the incremental rendering that ERNST offers, we need to have a fair amount of processing horsepower in your studio. We can install Beasts on other machines in the office, borrow cycles from them, but what we're adding here is the ability to render in the Autodesk A360 cloud. So at first we'll move the final bake process to the cloud, but eventually, towards the end of this year, we're going to have ERNST Preview in the cloud. So you can do everything we saw without a render farm, without a lot of compute resources in-house. And let me just finish by briefly showing a video of Hyperspace Madness, which is a demo we've done here. And it combines all of the Autodesk suite of Gameware products, but I'd like to emphasize the lighting, so I'll just let that play here. That's all we have for you today. Are there any questions? All right, well, thank you very much for your time.